Hello, everyone. This is chapter 8 of our quantum series workshop. My name is Gwen from Eve Count Quantum Systems, and today we are talking about quantum error correction, also known as the shield. So, we know the adversary, noise. We know it's fragile. Now, we build the shield. So we're gonna talk about the QEC or quantum error correction paradox, right? Because classical error correction is easy. You clone your data, you write zero as triple zero, and take a majority vote. But as we learned, the no-cloning theorem forbids us from copying quantum states. This is our dissonance. Our solution cannot be cloning. We need a new, non classical kind of redundancy to strike it out. So we don't need to fix every possible error. We're just taking a look at decomposition. We actually only need to fix the fundamental errors. Any single qubit error can be decomposed into three poly errors: bit flips, face flips, or both. So if we can design a code that corrects those, we can actually correct anything. So there's something called the Shor 9 qubit code, which is kind of like one of the main earlier breakthroughs, and a hybrid approach against protecting both flips. It was costly, but it proved it was possible at the time. So let's take a look at something called the threshold theorem. This leads us to the most single important result in the field considered by most. It's our pass fail grade. It states that if the hardware error is a rate that's below a certain very small threshold, we can perform arbitrarily long reliable computation. And this is kind of like the holy grail here. If we're above that threshold, noise wins. It's kind of simple. So you can actually build a shield, but shielding has a cost. And in the next chapter, we look at stopping not just errors and start looking at the economics of the information itself.